In this video, we answer the question of what an frequency response function is, what it tells us about the mechanical structure, and why it is so relevant to practice. Every rotating machine produces an unbalanced force. This cannot be avoided. As an engineer, you are interested in how your system responds to this harmonic force excitation and how the system properties shape the dynamic response at different excitation frequencies. The rotating machine shown here can be simplified as a single degree of freedom oscillator, which can be excited harmonically into vertical vibration by the unbalanced force. The equation of motion with the force F and the degree of freedom Z is mz double dot plus dz dot plus kz is equal to F hat times e to the power of j omega t. Since this is a linear system, it can be transformed using the Laplace transform, which leads to the following equation in the frequency domain. ms squared plus ds plus k times z of s is equal to f of s. We can now write this equation as the ratio of the complex output quantity, which in this case is the vertical displacement z, to the complex input quantity, which in this case is the harmonic force excitation F, and we therefore obtain the transfer function g of s, which in system theory is sometimes also referred to as h of s. Z of s over f of s is equal to 1 divided by ms squared plus ds plus k. Here, this ratio is called the receptance, which is the inverse of the dynamic stiffness. So, how much does the structure deflect under a dynamic force excitation? This ratio between the output and the input quantity is referred to in structural dynamics as the frequency response function. It consists of the amplitude amplification, described by the magnitude of the frequency response function, as well as the phase shift between the response and the excitation. You can find the exact derivation and transformation using complex conjugate extension in the video linked above. By substituting s with j times omega, we obtain the frequency response function as a function of the three system parameters mass m, damping coefficient d, and stiffness k, as well as the excitation frequency omega capital. This is the complete description of a linear dynamic system and provides, in an extremely compact form, the system response for any arbitrary excitation frequency. We can now plot the two components of the frequency response function over the excitation frequency. For linear systems, the curve usually looks like this. By the way, more on structural dynamics, modal analysis, and vibration engineering you can find in the full playlists linked at the end of the video. Subscribe if you want to follow the series. When the excitation frequency omega capital corresponds to the natural frequency omega 0, the response of the system is shifted by exactly minus 90 degrees, meaning it lags behind the excitation. The maximum system response occurs at the damped natural frequency omega d, which is lower than the undamped natural frequency omega 0 due to the damping. For excitation frequencies much higher than the eigenfrequency, we are in the so-called isolation region or decoupling region. In this region, the inertia of the system can no longer follow the high-frequency excitation, and the system response becomes smaller and approaches zero as omega capital approaches infinity. In the static case, on the other hand, the magnitude of the transfer function is 1 divided by k, which is nothing other than the static compliance of the system, meaning the compliance when omega capital equals 0. The phase lag in the static case is correspondingly 0 degrees because there are no dynamic effects. Now let us interpret the whole frequency response function mathematically in a different way once again. For omega capital equals 0, only 1 divided by k remains. The system response is then the transfer function multiplied by the input signal, so Z is equal to 1 divided by K times F. We can now also describe the frequency response function through a few small transformations as a function of the frequency ratio eta, meaning the excitation frequency divided by the natural frequency. With that, you can clearly see that in case of resonance, when eta is equal to 1, only the damping ratio D in the denominator prevents the response to become infinitely high. In the real world, every system does have damping, for example due to friction. However, in modeling, you can recognize damping that is too low by very sharp and narrow peaks in the amplitude plots. When the excitation frequency approaches infinity, the denominator also approaches infinity, and therefore the amplitude amplification approaches zero. The representation using the frequency ratio has another major advantage. The frequency response function is divided into two factors. The first is solely the static deflection, 1 divided by K. The second one is the dynamic magnification factor, which K is the static deflection and tells you how much more the system deflects due to the dynamic effects. With this, the frequency response function magnitude plot starts at 1 for omega capital equals 0, because this is the quasi-static case. The qualitative behavior remains the same. Only the scaling changes, and we obtain the information of how much more strongly the system will oscillate due to the dynamics compared to the purely static loading with the same force amplitudes. Let us summarize the most important points. The frequency response function gives the structural response to an excitation across all frequencies. It is derived directly from the equation of motion under harmonic excitation by a Laplace transformation. The phase shift is equal to -90 degrees at the undamped natural frequency. At eta is equal to 0, we are in a static case, and the amplitude of the response, Z hertz, is equal to F hertz divided by K. At eta is equal to 1, we are in resonance, and only the damping limits the amplitude of the response. At eta is very large, isolation through the inertial cues